Okay. Being able to predict acid and base strengths is really kind of what today's all about. And acids and bases, they can be misused, and they don't have to be strong to do it. You don't brush your teeth, I mean, it's kind of disgusting, but that's what can happen. So what is in soda that's acidic? Anybody ever read the little label? There's acids in there, right? Phosphoric acid, there's some citric acid, there's a whole, when you pop the can open here, what gas is that? Carbon dioxide. So that means a lot of that carbon dioxide is dissolved in the water that's in the soda. If you dissolve carbon dioxide in water, you get another acid. What was it? Carbonic acid. So there's a lot of acids in soda. And then there's also the danger of, the concentrated stuff. But if you use acids and bases correctly, I mean, it can really make life a lot better. I mean, so that's just, they're all around us. Okay?
What?
Oh, my base side is like egg, toothpaste. I don't know what the heck this is. Some kind of cleaner or something. No, I'm a thief. Everything's off the internet.
I thought. Why did they say don't?
They should be.
Why did they tell you not to brush your teeth?
Oh, no. That's supposed to be in your mouth. You should do this. Maybe that's a reason why it really helps. Right? Because the acids are eating away the enamel. I never noticed that, although. Maybe that's why this Colgate has basic properties. Acids that cause the problem in your mouth.
Well, I'm saying, that makes sense, but people say don't brush your teeth after you back your teeth.
What? No. I don't know who you're talking to. You brush your teeth all day, every day, and this is better.
That's right.
You have some weird friends, Aldo. Okay. Oh, we're supposed to talk about strong acids. I've got an animation to show you some strong acids here. Okay. We've mentioned hydrochloric acid as a strong acid. So they're bubbling hydrochloric acid, HCl, into the little beaker. And then they're trying to say this is what's happening at the molecular level. Right? And that these little HCl molecules, they all break up into chloride anions and these protons floating around. But Javier, whenever the last class period was, Wednesday, there's something wrong with that animation. You can't have little bare protons floating around. It's you hear them? It's the hydronium ion. You can't have a bare proton floating around. They should have hydronium ions floating around. There's nothing wrong with the chloride anion floating around. So it's a good animation in the sense that they show that there's no HCl molecules anywhere. The word you're supposed to use is dissociate. They completely dissociated. HCl does not exist in water. It's all protons. It's not protons. They're hydronium ions, anions. Okay. But if you take something that's not a strong acid, hydrochloric acid, and bubble it in water, there's what's going on at the molecular level. Now, it's supposed to be an acid, so you better get some dissociation going on there. And there's one that's trying to indicate, there's a little bit of dissociation. But again, you shouldn't have a bare proton floating around. It should be a hydronium ion. Yeah, it's a weak acid, so everything stays together. It doesn't dissociate at all. Once you have a weak acid, it stays that way, right? So you could say the equilibrium is dominated by the presence of HF. It's all in the HF form. There is some fluoride and some H+, but it's very, very little. Okay? So the equilibrium is dominated by the weak acid. That's the terminology we need to get used to. What I mean is the HCl molecule doesn't exist. Inside that little bottle, there's HCl, because HCl molecule, gas. But once it goes into water, it completely, what's the word you're supposed to use? Starts with a D? Dissociates.
So that's not regardless of the molarity.
Yeah, it doesn't matter. I mean, you dump in a little bit of HCl, it all dissociates. Dump in a lot of HCl, it all dissociates. It just becomes a more and more acidic solution, is all. More concentrated. Strong acids are, Eddie, what in water? What percent? So half those HCl molecules were floating around in the water. Not 50. It's 100% dissociated. Strong acid. 100%. Doesn't matter what the strong acid is. 100% dissociated. So that means we probably should know the names and formulas of the 6 strong acids. Ray, one was in the animation. HCl. Hydrochloric. Okay. I'm here at Adrian, but he's using the periodic table to give half of the 6, to give 3. You look at that group, right? The halogens, HCl. Just don't pick which halogen? Fluorine. Don't pick HF, because that's a weak acid. So HCl, he said. HBr. HI. So HBr wouldn't be hydrochloric, it'd be hydrobromic. So they're not so hard to name. Hydrobromic. And hydroiodic. Okay, there's 3 more. Amanda, do you know another one? We used some in lab. I think. Maybe. Well, we use hydrochloric. Ooh, sulfuric. H2SO4 is another one. Sulfuric. Anybody know another one? Ooh, you get HClO4. Perchloric. There's one more. I think this is the most dangerous acid, HNO3. It's the most dangerous acid. The reason being because you don't feel the burn until later. So that stuff is all over you in the lab, and then you start feeling the burn. And that's not a good thing. Nitrogen. Okay, so there's 6 strong acids. Now, weak acids, how do you know if something's weak? Lewis, how would you know if everything's weak? Is Smith going to make you memorize all these weak acids? It's just your problem. It's just everything else. If you know the list of 6, then you know all the weak acids. Because if it's not one of the 6, it's weak. Right? So that's how it works. It's not one of the 6. Okay. In general, I am writing a strong acid, Bobby, as HA. So this strong acid breaks up 100% into what and what, you'd say? H and, well, H, technically, H plus and A minus. Right. Okay. Now, there is no backwards arrow on this, Jessica. Vaughn, why? Yeah, because it's a strong acid, right? That's the words that they want to get you used to. Is this is super, super strong, so it completely dissociates. This A negative is super, super weak. Super, super weak. That's a base. A minus is supposed to be a base. It's supposed to react with H plus. But it's so weak it can't do it. So there's no backwards arrow. We'll mess with that a little bit more in a little bit. That's our proton. Now, we're not supposed to write protons, though. We're supposed to write hydronium ions, so you could also write the react, well, H3O plus A negative. This is probably technically that's the best way to do it. In fact, we're not really done, because we should be writing little subscripts on this stuff. What did AQ mean? Aqueous. But we just get lazy. All right? That's really how the whole thing should be written. But I think we're going to be writing everything the top way, because it's the same thing. It's chemically the same thing, so we'll be lazy the rest of the semester. But
In the top of there,
yeah.
Would you also like assume that there are water?
Yeah. So we should have a little AQ on there. Yep. We should, but that's what I'm saying is on the top one, we're going to be lazy and we're just going to write everything this way. We're not even going to be writing hydronium ion because the book doesn't, and it's technically the exact. You get the same answers, and it's easier. It's less things to worry about. You have to be writing plus water all the time. So I just wanted you to realize what's technically correct and you don't get surprised. Okay. Alexa, we've got this big table of conjugate acids and bases. Now, we had, last class period Wednesday, we had 3 theories on acids. Whose is this one? This idea of this conjugate pair stuff? Now, Lewis was the electron. Bronsted and his buddy Lowry, right? Bronsted-Lowry. So looking at this table, which conjugate acid, Pablo, is the strongest? What compound is the strongest acid up there?
No. Perchloric.
HClO4, perchloric. What is the weakest base up there, Jessica Rojas? ClO4 minus, perchlorate. Okay. Do you see why? Who wrote this out? HClO4 goes to H plus and ClO4 minus. We're saying that this is super, super strong. So it goes 100%. So you can think of the perchlorate being really strong, the perchlorate anion being really, really weak. Okay, so it's the same idea. So what, in general, it's true. The stronger the conjugate acid, then the Sylvia is conjugate base. The weaker. Yeah, that's how it works every time. Do you notice 2 on this table? Do you need to memorize those 6 strong acids, those formulas? Yeah. They're up there. Yeah, look at the top 6. Right? There they are. So, you don't have to read the table. You really don't need to memorize them. Okay. Let's see if we can play around with the table a little bit, though. Which acid is stronger? Matteo, H2S or H2SO3? Because H2SO3. I found it here. Where's H2S? Oh, it's lower. He's right. Right? Okay. How is there something, can anybody see something that can act like an acid or a base? So it needs to be in both columns. Is that even possible? Ooh, I hear HS negative. That's on both sides. There it's here. Halfway up. Oh, there it is. All right. It's on both sides. Anything else that's on both sides? Oh, H2O is on both sides. All right. There's several compounds that are on both sides. They can act like an acid or a base. Okay. Well, no, they can. It's going to. We're going to see it in a little bit. It's going to depend what it's reacting with. But it can act like an acid or a base. It depends on what it's acting with. That's going to determine whether it acts like an acid or a base. And that's going to become. We're going to see that in a little bit here. But I think they are the ones that confuse everything. So they make it. You have to think now because of them. So let's see if we can get into this predicting acid-base reaction. We want to predict the products, and we want to predict the direction. Okay. Now we remember from before that an acid always reacts with a base, and then these guys are, what's the word? Conjugates. Right? They're conjugates. Now the direction, though, we have to draw directions in these reactions. We're going to predict the products, and then we got to draw a direction. Okay, which side does the equilibrium lie on? It's mostly product or it's mostly reactant. Well, you always draw the arrow towards the, I hear weaker, and I hear strong. He's got it. You hear Aldo? You draw it towards the weaker because he doesn't go back. Once you form that weak system, that weak acid, he's not going to go back. He's going to stay there. So it's always the weaker acid. Exactly. Okay, let's try a few of these. H2SO3 and HS-. We're supposed to predict the products and then the direction. Okay, now, Shelby, the idea is you got to recognize we're going to have an acid and a base on both sides, and they're going to be conjugates. The trick to doing this, in my mind, is to find a compound in the problem that has no choice. It has to be an acid, or that compound has to be a base, and that's where you start. And the reason why is, let's say you found out that this guy has to be an acid. Well, then everything is fixed. He has to react with a base, and then this conjugate's on the other side. Do you see one in A that has no choice? Shelby, do you see one that has no choice? It's H2SO3. Now, there's a couple ways to recognize it. One is, if you remember the name, what was that anion called? Not sulfate, but sulfite. It has a -2 charge. What's the maximum number of hydrogens you can stick on that anion? 2. The word is fully protonated. You can't get any more protons on there than 2. So when Shelby looks at this thing, she says, oh, that's maxed out on hydrogen. That has to be a acid. Now, we don't know. Well, it's not on the list of 6. It's not strong. But it has to be an acid. It's got all the protons it can get. Because if it was a base, it has to grab another proton. Well, it can't grab another proton. It's maxed out. So this has to be an acid. Well, that means HS-, everybody has to be acting like a base. And that fixes everything. Because then we know we have to draw the conjugate. Also, the conjugate, right, this has to be a conjugate base. What's the conjugate base of H2SO3? HSO3. With a what charge? With a minus. Right? We have to move an H+. And then we need the conjugate acid of HS-. And that's, everybody, H2S. Okay. Oh, I have a bad habit. What's my bad habit? This thing, I don't know. I mean, I have a 50-50 shot of getting that right. Better erase the damn thing. I'm supposed to point the arrow at which acid? The weaker one. You got to look at the table and compare which 2 acids, H2S, H2S. Compare these 2. Was I lucky? Really, H2S is weaker? Oh, okay. H2S is weaker. Okay. Adrian, we've got B, and both minus and HCN. We want to predict the product and the direction. Where would you start? Now, hang on. He says HCN is the acid. Do you? So what we're trying to do is find something that has no choice. Right? Because remember, we memorized all these guys. What was CN? Wow. At a -1. The maximum number of hydrogens is 1. Once you get HCN, it's fully protonated. That's the acid form. It has no choice. He's right. So that means HS minus must be acting like a base. All right? Oh, you could. You could deduce it from the table. You would look through the table and see if you can find an H2CN. See if you can find an H. No. Oh. No. There's more than one way to. Right?
If you go based off of the list, the HS minus is the.
Yeah, that's the problem. The HS minus goes both ways. But, all right. Okay. So, there's, like I said, there's probably more than one way to figure these out. But to me, I do it the most logical way. And the most logical way is if you start, because then I don't need to even look at the table. Exams, quizzes, life, you're not going to have a table and you don't have so much time. So go by logic. The less stuff you have to memorize, the better. Right? So you find this, which one doesn't have a choice? You already know the answer to that. That's what I'm trying to get at. You already know HCN is cyanide has CN minus. HCN is, that's it. You can't get any more protein. Okay. So then I'm going to have to do the product. Right? I have base. And I need its acid. Okay. So the base of HCN, everybody? CN minus. And then I need the acid for the HS minus, conjugate base, H2S. The arrow, I got to compare what two acids? HCN and H2S. And which one's weaker? HCN's weaker. Oh, I don't. I believe you. HCN's weaker. Point it towards it. Okay? Not too bad. Just identify the compound that has to be an acid or a base, and you'll be set. Everything else falls into place. Yes? Look at all the different forms of the sulfide system. You've got that, you've got this, and you've got that. So HS minus could go either way. It could grab a hydrogen and form that. Or it could go this way and form that. That's the problem. So you don't start with the guy who, right, can be an acid or a base. Predicting acid strength from molecular structure. So if you're going to be, I don't know, working in a lab making compounds, these are just some guiding principles. We have this bond they're trying to say. HX. So H is supposed to be the acidic proton that falls off. And X is everything else. Okay. If you're in the same group in a periodic table, Destiny, what were the groups? Were they the columns or the rows in a periodic table? The groups. They're the columns, right? Because remember, you had the halogens, you had the noble gases. They were all the groups. Okay, so if you're talking about a group, so I have to be these in the same group when you're comparing these acids. And you have larger elements. So now this bond is spread out over a larger area. That's going to make the bond weaker or stronger? Weaker. Because now, right, it's sharing electrons spread out over a larger area. The bond's weaker. The bond's weaker now. That proton can fall off. Just so much easier. Just slough off of there. Because the bond's weaker. Well, if the bond's weaker, then the acid strength is going to be stronger, right? So now it's much more acidic. It's a much more acidic solution. So a weaker, whatever you do to weaken that bond, it's going to make it a stronger acid. Because that proton can fall off even easier, dissociate even easier, to a higher degree. Now if we're talking about the same period, right? The same period. This one is tough. And it's really hard, I think, for you to see it. The answer is stronger. The more polar this bond becomes, the more acidic and the more acidic properties it has. Okay. Now, the bottom one, though, you might be able to get that one, because a lot of those strong acids that we're supposed to know, there's a lot of oxygen. The more oxygens, then the stronger. Like, look at perchloric acid, 4 oxygen. Nitric, 3 oxygen. Okay. Okay, let's try some of these. So that table is the one with all the conjugate acids and bases. We're supposed to decide whether we're draw the arrow to the right or the left here, reacting towards the reactants or products. So Mallory, where would you start, right? Because the idea is to find out what's acting like an acid and point the arrow towards the weaker acid. So where would you start in figuring this? Doesn't have a choice. That has to be an acid or it has to be a base. That would be our starting point. What could you pick? Yeah, something up there has no choice. It's this way every time. Now H2O, remember H2O is the one that's on both sides. So you can't pick it. Don't buy any lottery tickets today. HCO3, look at that. Look, that's on both sides too. Think. Okay, that's one way. We know that hydroxide's a base. So you could just go at it that way, right? Or you can go at it Smith's way. There's no hydrogens with the carbonate. Carbonate has to be a base. It has no hydrogens. So that's another way to go about it. So I see 2 starting points. 1, either you call this a base, or 2, you call this a base. And then everything else falls into place after that. Okay? The reason why you can't start with the water or the bicarbonate, because they can be an acid or a base. Okay. So which one do you want to start with? For C. You want to start with carbonate. Okay. So we're going to call this a base. Everybody, that means water has to be a acid. Okay, let's connect our conjugates. These guys got to be conjugates, and these conjugates. So the hydroxide must be a... Yeah, because it's a conjugate to an acid. And plus, you know it's hydroxide, right? And then the HCO3 minus must be acting like a acid. Identify the 2 acids to compare. Which one is weaker?
H2O.
H2O is weaker? Okay. Always goes towards the weaker. You said why? Although, right? Okay. Let's take a look at D. Vanessa. Where would you like to start? You just find something that has no choice.
Well, on this test, I think that we
Did I forget the +3? Oh, I did. I forgot the +3. Okay. Acid. And you're using the table. Is there a way not to use the table? Because what if I didn't give you the table? The OH, right? But if you use the table, I agree with you. Want to have it accessible or something. You're right. Okay. And connect these guys. See what's what. So he has to be a base. Identify the 2 acids. It ends up pointing towards reactants or products that dominate at equilibrium. Products. You're saying water is weaker than that aluminum complex thing. Okay, everybody agrees. Try these. Try those. See if you can identify draw in the arrow. It shows, hey, oh, the reaction's really going to go towards in this direction, dominate. If you're not sure, just ask. I'll be glad to help you out. So find something that has to be acting like an acid or a base. It has no choice. That's your starting point. Yeah. So that means he's his conjugate and he's his conjugate. Yep. So acid, conjugate, conjugate. And you compare the acids.
Are we supposed to be drawing the...
Okay. What? Yeah, but he has no choice because he's fully protonated. If you remember sulfide, it really helps because S negative too.
Are those all right the way it was?
What do you mean? I don't. I need the table. I need to compare.
Oh my God.
Now in B, there's a couple things you could. If you remember sulfide, 2S then is fully protonated. That's the maximum number of hydrogens you can get. You could do you could do the same thing with the carbonate. Right? That's maxed out with carbonic acid. That's what carbonic acid is. That's maxed out with 2. There's 2 starting points for for B, I think. You could call this an acid, or you could call this an acid. Yeah, it kind of means like it's all going to be those. The one it's pointing to is the one that is going to be the most of at time. That's why it always points to the weaker system, because once you form that weak guy, he stays. He doesn't dissociate. Okay, so did you get answers for these? Let's pick on Victoria. What did you say for B? You had to compare H2S and H2CO3. Which one's weaker? H2CO3 is weaker than H2S?
H2CO3 is stronger, so it goes to...
Oh, it's the other way around, Victoria. H2S is what people are saying is weaker than H2CO3. How about in C? Javier, you ended up pointing what dominating at equilibrium? The reactants or the products? He says they're reactants. Everybody agrees. How about D, the last one, everybody? What's left? Reactants? They're all going towards reactants, huh? Yeah. Okay, I believe you. Last. You might be able to get the answer from the table, but it's not going to really help explain why. So, H2S or HS minus. Eddie, one of those is strong. Which one would you say is stronger? Now, he's right, but why? What can you say why? It's maxed out, fully protonated. Yeah. Well, that might be it sounds the most, right? How about B? Ray, we've got H2SO3 and H2SeO3. They both have 2 hydrogens. There's the oxygen story, but they both have 3 oxygens, so that doesn't work either. They are. You see sulfur in that periodic table? You've got sulfur, then right below it you have Se. So which one? That's the bigger story. Which group is the bigger story? Which element is bigger? Se. So that means which bond is going to be weaker? The one with Se. So that means which one is stronger? The one with Se. Group is the size story. Last one, which one's stronger? More oxygen. Right. Good. Because selenium is bigger. Bigger, so that means weaker bond. And that means stronger acid. Okay. So if you can make it to the speaker, that'd be great.